I think we ought to get started. Recording, yes, good. So let me share. We're going to look at the review documents, and there are two of them, one for each chapter, my chapter 10 and my chapter 11. Both of them together cover your chapters in Brown, 11, 12, and 13. So let me take 10. Here we go, share that one. There we go. Now, that's good. All right, so I've selected some of these. We're not going to do all of them, but I've selected quite a few of them that address main topics and issues that you would be concerned with for the upcoming exam, which will be due by midnight next Friday. Of course, once we finish with this review, the exam will open up and it will be available. Let's see, did I do it that way? Or did I make it dependent on completing certain tasks? No, it should be open by dates. So when we finish this today, this review, the exam will open up, and between now and next Friday, at your convenience, just go ahead and take the exam. It's in Blackboard, and you have to use your lockdown browser and go through some steps to satisfy the respondus monitor. Let me check just a second to see if I made a note of that. No, I didn't. Okay, there's a practice test in Blackboard. So if you go to lockdown browser and then do everything right there, then go to find the test. It's a practice test. It's got one question in it, and it really doesn't matter what the answer is. It's just for you to test your equipment and be sure that everything's working, so that when you start the exam, your first exam, then you'll know that everything should work, and that once you go into it, you won't have any delays or anything to distract you from taking the test. Okay, so let's take a look at chapter 10, first one. Let's do number 1. Which of the following should have the lowest boiling point? So let me get things organized here. This will be for my chapter 10. And we'll do number 1. Okay. So what do we have as our choices? We're going to compare these and try to determine qualitatively which should have the lowest boiling point. We don't need to know exactly what it is, but we compare them based on what we know about how intermolecular forces cause different behaviors, and those, in this case, relative to boiling point. So we have sodium sulfide, and we have hydrogen fluoride. Of course, if that's in aqueous solution, changes the name. Then it becomes hydrofluoric acid. Actually, you know, if we're talking about boiling point, these are pure substances, so that's not going to be in solution. It's going to be a gas at 1 atmosphere and room temperature. of water. Okay, so if we're just looking for the lowest boiling point, what condition contributes to boiling point? Well, what are the attractive forces among the molecules of the compounds? Well, we can start from the bottom. What attractive forces do you have here? Well, the intermolecular forces are, and these are pure substances, so it would be polar-polar interaction. All right, so this would be polar and polar. So that's one molecule, that's the other molecule. These molecules are polar, so they'll orient themselves slight positive to slight negative. Nitrogen. What are the forces that are available for nitrogen? It's not polar, so the only thing you have available are London dispersion forces. How about ammonia? Maybe I drew that one for you, maybe I didn't. Oh, but this is second semester, so you should know already that ammonia is like that. So it's polar. It's not as polar as water, but it's polar. So how about HF? Well, HF is a molecule. It's a covalent compound. So it's going to be slightly negative here and slightly positive there. So that's a polar interaction. How about Na2S? You got a metal and a non-metal. This is an ionic compound. So the interactions there are ionic. That means the boiling point for this one is the highest of all of them. But the question is, which is the lowest? So we need to find the one that has the weakest intermolecular forces holding them together. And it turns out those are the weakest London dispersion forces for nitrogen. That's why the answer is D. Okay? You know, Brown doesn't want to come off of there very well, does it? All right, number 3 is the next one I'm going to look at. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Okay, what are our choices? A says a hydrogen from one molecule and a hydrogen from the other. Well, look at the water molecule first. What contributes to hydrogen bonding? Okay. First of all, in order to have hydrogen bonding, you need a hydrogen. But the hydrogen needs to be bonded covalently to one of 2 or 3 electronegative atoms. Oxygen's one possibility. Another one is nitrogen. And I contend sometimes sulfur even. But what does that do? That makes this end negative and these positive. Right? So there's your water molecule. So when they come in close proximity to one another, are you going to get an attraction between 2 hydrogens? Hydrogen on this one and hydrogen on another one? No, they're both positive or partially positive. So that's a repulsion. So A can't be it. How about B? A hydrogen from one molecule and an oxygen from another. That one fits the bill. All right. So under these circumstances, you found the right answer, you can stop. Right? Because B's right, and these others can't be right. An oxygen from one and an oxygen from the other, no, they're repelling. an oxygen and a hydrogen from the same molecule. No, they are sterically hindered from moving, right? It's not going to move around here and attract one another because they're already interacting in such a way that electron density is being pulled away from that hydrogen. So they're not going to interact because the molecule's too small, can't bend around. Now, if we were talking about a large molecule, extremely long one, which had potential for hydrogen bonding on one end and hydrogen bonding on the other, then it could conceivably wrap around and interact, and they do that. But in this case, the molecule is too small. It will never happen. So that's why the answer is B for number 3. All right, so let's flip the page. I'll do my hard copy flip, and then I'll move this one down to get to number 4. There we go. So consider these drawings. And notice that we have atoms linked together to form molecules, it appears. And then there's going to be a question about one of them. That's number 4. Which of the following statements are incorrect concerning drawing 3? So we only had to focus on drawing 3. Right? So either, well, one of them could be incorrect, or we have an item down here, 2 of the above are incorrect. So we got to look at each one of them to see if there are 2 that are incorrect. All right, so let's look at what we've got here. It looks like we have a chlorine and a hydrogen bound together. All right, and there's a slight redistribution of electron density that gives you a negative toward the chlorine and a positive toward the hydrogen. Okay, so what do we have here? We've got a polar molecule with the potential for polar-polar interactions among the molecules. So now let's look at the statements and see which one's false. Electrostatic interactions exist between the molecules. Is that true? Electrostatic interactions don't necessarily require that you have a complete charge separation. In chemistry, as long as there is an uneven distribution of electron density, then you can get separation of charges, so you have positive, negative, even if it's very slight. And then you can still have electrostatic interactions. So A is true. How about B? The molecules find the best compromise between attraction and repulsion. That's another way of saying that the substance, in this case the compound of HCl, tends toward the lowest possible energy. And that's a true statement. This is another way of saying it. They find the best compromise between attraction and repulsion. C, these molecules exhibit ionic bonding. What would you need for ionic bonding? You'd need separate ions. So you'd have to have an H plus and a Cl minus separate from one another. But they're not. They're bound together, and you only have a slight charge. That does not form an ion. So C is false. Now, in order to eliminate E, we've got to see if D is false also. If D is true, then we've got our answer at C. OCS, that is a compound. Okay. Now, that's not the proper Lewis dot structure for it, but what we need to do is figure out what the Lewis structure is, because Well, even if it's linear, right? Look at that. Even if it's linear, carbon in the middle, oxygen on one side, sulfur on the other. What's the electronegativity of oxygen versus sulfur? Let's look at your chart. Sulfur is below oxygen, so it would have less electronegativity. Oxygen would be greater. So that would mean that you would have a dipole this way and a dipole that way, but overall you would have a dipole this way. So you would have slight here and slight positive there. Okay? In this case, we don't care about symmetry. Symmetry would just add to the polar nature. But even if it were linear, you would still get a dipole toward oxygen. That means that you have a polar molecule, and you could also have similar interactions for this molecule as you do for the one that's given in the diagram. That means D is also true. So the only one that's wrong is C. Okay, so the next one I want to look at is 5. Actually, 5, 6, and 7 on the next page. All 4 of them. 7 and 8 also. 5. Okay. So far, we're doing qualitative interpretations. We haven't solved any formulas. We haven't done any calculations. And I don't think we need to for this one either. The freezing point, let's see. For the benefit of our video watchers, the freezing point of helium is minus 270 degrees C. So freezing point of helium is minus 270 degrees C. And the freezing point of xenon is minus 112. Oops. Okay, that's given. Both of these are noble gas. Same families. Which of the following statements supports these data? Helium and xenon form highly polar molecules. No, they don't. In fact, they don't even form molecules. They're individual atoms. So A is false for 2 reasons. B, as the molecular weight of the noble gas increases, the freezing point decreases. So what's the molecular weight? Well, actually, it's the atomic weight. The atomic weight of helium increases from here to xenon. And the statement says, as that increases, the freezing point decreases. Actually, the freezing point increases. Okay? The trick there is to watch that negative sign. The freezing point increased from here to here because it was less negative. Okay? That could throw you. So that means B is also false. The freezing point actually increases as the weight increases. C, London dispersion forces between the helium molecules are greater than the London dispersion forces between the xenon molecules. All right. What does that mean? If the intermolecular forces are increasing, that means the atoms are being held more tightly together, which means that the freezing point should increase. Yeah. Another way to look at it is boiling point. I mean, not freezing point, not boiling point, melting point. So if they're held more strongly together, they're less likely to melt. It takes a higher temperature. So it takes a higher temperature for this one than it does for that one, because the London dispersion forces are stronger for xenon than they are for helium. So C is also false. D is the other way around. London dispersion forces between helium are less than those for xenon. That is true. London dispersion forces for helium are less than this one. So you have to get helium colder for it to condense. That's true. So D is the answer. All right, how about 6? Okay, 6. Which best explains the following trend? All right, what's the trend? Well, we've got elements, and they're listed, the noble gases are listed in this little table from helium to xenon, and the boiling point is actually increasing as we increase the mass of the atoms. And these values are in Kelvin, right? So helium is 4 degrees Kelvin, 4K. We don't say degrees. 4K for helium, and xenon is 170K. So you're increasing. In fact, helium, I think helium is the coldest substance. Liquid helium is the coldest substance that we've been able to manufacture, in large quantities anyway. So what explains that? I mean, are there any possibilities for hydrogen bonding? No, there's no hydrogen. Any possibilities for dipole-dipole? No, because it's a single atom. The only possibility is London dispersion forces. And Le Chatelier's principle was thrown in there just to confuse you. London dispersion forces are the explanation for an increase in boiling point as you increase the mass. There's no other possibility. Those are the only forces available. So that's why A is the answer for 6. Seven. Which of the following compounds has the lowest viscosity? So let's write this one up here. A, B, C, D, and E. Okay, so we have, what's that one? Carbon tetrachloride, liquid. Nitrogen, gas. Water. And this one. And let's see, it's 25, excuse me. 25. And that one. And that's a liquid, of course. And this one, which is a gas. Okay, this one might throw you. This is a hydrocarbon. It's got a long chain of carbons, and then off each carbon are hydrogens. If they're not connected to the carbon next to them, all the other positions are hydrogens. And this is probably, this could be a component of diesel fuel, or it could be getting close to asphalt. There's a braking line in there. Anyway, what's the question? Which one has the lowest viscosity? So before we even look at that, we know that viscosity is a resistance to flow, right? And solids are generally not considered because they don't flow unless they're under enormous pressure, like deep down in the crust of the Earth, solids will actually deform. But there are no solids there. There are liquids and gases. So what's the viscosity of a liquid? Well, the viscosity of a liquid depends upon the intermolecular forces, right? What's holding them together. The stronger the forces, increase viscosity. So if there were only liquids here, then we would compare that one, and that one. And we would determine that the viscosity of this one is the highest. But we have a gas there. And the viscosity of gas, while measurable, is vanishingly small. Gases are virtually non-viscous. It's easy to move a gas through a mesh with virtually no resistance. There is some resistance, I'll grant you. But compared to liquids, it's nothing. So the gas is the least viscous of all of these due to its phase, plus due to the fact that there's nothing holding them together but London dispersion forces. Okay, so answer 6 is B, nitrogen gas. 7, excuse me. Yeah, 7 is nitrogen. Okay, 8. Let's finish this page. When a nonpolar liquid displays a convex meniscus, all right, let's draw a picture. So when would it display a meniscus? When it's in a narrow tube. So it would form a convex meniscus. All right, there's your tube, there's your liquid, right, like that. That convex meniscus says what? How do we explain the behavior? Well, remember when we discussed there are competing forces involved here. There are the cohesive forces. Those are the ones that are drawing the liquid into itself, forces among the liquid molecules. And there are adhesive forces. Those are the ones where the liquid is attracted to something else. And the only something else here is the walls of the tube, right? So when those two compete, one of them usually wins. And the evidence for that, what we see in the tube, is the meniscus. If the meniscus is convex, that means that the attraction between the liquid and the tube is less than the attraction between the liquid and itself. So in that case, cohesive forces win, adhesive forces lose. The other way around, if the meniscus is the other way, then the adhesive forces are stronger than the cohesive. Okay, so let's see if we can find one of these statements that satisfies that explanation. It has a low surface tension and therefore clings to the glass. Low surface tension is the tendency of a liquid to resist an increase in surface area at the surface of the liquid. So that would tend to, see, because that's, meniscus has a certain surface area, but if you can flatten it, you have less surface area. So that means the surface tension would be higher. Low surface tension, that is a possible explanation, but it's not the best one, right? Remember in multiple choice tests, pick the best answer. So we'll hold A in reserve in case B, C, and D, and E don't work. How about B? The cohesive forces are stronger than the adhesive forces. That's true. In fact, that's a better explanation than A. C is just the opposite, so it can't be right. And the liquid's viscosity is low. Low viscous liquids tend to form no meniscus at all. And there are very few of those examples. So the best answer is B, when you show the competition between cohesive and adhesive forces. All right, so let's see, where do we go next? I've already used up a half hour. Let's see if I can get the rest of this done in another half hour, so it leaves us chapter 11 for an hour. Okay, let's see. Which one else did I select? 9, 10, and 11. All right, maybe we can knock these out quickly. Number 9, which substance can be described as cations bonded together by mobile electrons? All right. This is one of the early explanations for how metals bond to one another. It's like metal ions with a positive charge in a sea of electrons. And then another metal ion over here with its electrons. All right. That's otherwise known as metallic bonding. So which one of these fits that bill? Well, the only one that can fit, our first choice is find the metals. Right? Sulfur's not a metal. Krypton's not a metal. KCl's not a metal. Well, it's a metal. It's a compound, actually. And the explanation for the bonding in KCl is ionic bonding, right? So that doesn't fit. And HCl is a polar compound. So its bonding is polar-polar. So really the only one that works is silver. Silver's the only free metal in this whole group that fits that statement. How about 10? Which of the following statements about steel is false? So it looks like they could all be true, right? E says all of them could be true. So all we need to do really is find one false one, and that knocks E out. How about A? It contains carbon atoms in the holes of its iron crystals. Is that true? As a matter of fact, it is. You have the iron crystals formed from iron atoms layered in their crystal structure, but the holes in between are small enough so we can fit carbon atoms. This is the alloy we call steel. The presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. That is true. The fact of the matter is, pure iron is very soft. You can scratch it with your fingernail. But steel is not. It's very hard. And the explanation for that is the special type of bond between the carbon and iron atoms. Right? The iron-iron bonds are not strong enough. That's why you can scratch pure iron. But when you stick the carbon in there, you've added that carbon-iron bond that is stronger, and it tends to lock those crystals in place so they don't move. That makes it harder and stronger. How about C? So A and B are true. C, pure iron is relatively soft and ductile. Ductile means you can stretch it into a thin wire. Soft and ductile because it lacks directional bonding. That's true. the bonding among the iron atoms is like the problem before it, where you have iron cations with electrons in a C. So there's really no directional bonding. You can move it, and it's just as happy to bond to the next one. You move it over, okay, I'll bond with whoever you want me to. So C is true. The amount of carbon directly affects the properties of steel. Oh, how true that is. There are different types of steel. High carbon steel, low carbon steel. Right. High carbon steel is anything that's in the neighborhood of 0.5% or less, and low carbon steel is going to be down in the neighborhood of less than 0.1%. So all of them are true. That's 10. How about 11? Yeah, that's on my list. Which of the following statements is true about p-type silicon? All right, now we're talking about semiconductors. So there's P and there's silicon. So normally in pure silicon, silicon would be in that position, and there would be no uneven distribution of electron density. But if we stick phosphorus in there, what's different about phosphorus than silicon? All right, see where silicon is right here. Right? If you move to the right, what have you done? You've added an extra electron in the valence shell for that position. So phosphorus has an extra electron that can be moved around. So that means a p-type silicon is, it provides a negative charge carrier. So let's see how the statements run. It's produced by doping silicon with phosphorus or arsenic. That's true. Arsenic, well, I made a mistake. P-type silicon. That's wrong. My mistake. Let's start with pure silicon. Back up. P-type silicon means there's a positive charge that can be distributed. Often called a hole because it's missing an electron. Okay, now a p-type silicon requires that you substitute one of these that is to the left of silicon. In other words, it's deficient in one electron. So which ones are those? Aluminum, gallium, boron. Those would be substitutions that could give you a p-type, right? Anything to the right will give you an n-type, negative type, rather than a positive type. Okay. So doping with silicon with phosphorus or arsenic won't work. It makes an n-type. Protons are the mobile charge carriers. Well, no. Protons can't be the charge carriers. Why? Because protons are in the nucleus. And if you move a proton, you have to change the element from silicon to something else. It can't happen. C, it does not conduct electricity as well as pure silicon. In fact, it conducts it better than silicon. And what we visualize is the positive hole moving around. But in actuality, it's electrons moving in to replace an absence position. So when the electron moves this way, the hole moves that way. So in fact, none of these are true. They're all false. Okay. Uh, 14. See what we got for 14. A solid crystal of sodium chloride is what? All right. So what's the nature of sodium chloride crystal? Well, you've got sodiums surrounded by chlorides. And then each chloride is surrounded by sodium. Right? On and on and on and on. In fact, each sodium is in 3 dimensions surrounded by 6 chlorides. And each chloride in 3 dimensions is surrounded by 6 sodiums. So that's where you get the NaCl 1-to-1 ratio, when in fact it's 6-to-6. But this is the empirical, this is the simplest whole number ratio. All right, so what do we know about ionic crystals? Well, we know that those ions are locked in place. They cannot move. Plus, the bonding is very strong in all X, Y, Z directions. So what does that lead us to as far as the conclusions we draw from 14? Oops, back here. Okay. Is it true? Solid crystal of sodium chloride is soft. No, it's not. It's hard. So A, C, and E are gone. They cannot be. We got to choose between B and D because the crystals are hard. Hard, hard, that's true. High melting point. Is that true? Yes, indeed. Very high melting point. B and D are still possible. B says good electrical conductor. D says poor electrical conductor. Which one's right? To be a conductor, you have to have mobile ions. And solid sodium chloride crystal does not have mobile ions. So D is the only one that answers all 3 correctly. Hard, high melting, poor conductor. All right, so next page. Ooh, I picked a lot of them out of this one. Okay. Which of the following has the highest melting temperature? Right? If it's a solid, then which one takes the most energy to turn it into a liquid? Okay. Highest melting temperature. Well, actually, not just the most energy, but the highest temperature. So what do we have here? Well, let's see. We've got a polar compound, which is normally liquid. CO2, which has very, very cold temperatures to make it into a solid. Dry ice, right? So that would probably have the lowest melting temperature, CO2. It starts off as a gas. S8, right? That's sulfur. MgF2, that's an ionic compound with a very strong bond. Remember what we said about what determines the strength of an ionic bond? One is the charge. This is 15. High charge, strong bond. So magnesium makes actually a 2+ charge. Fluorine's a 1- charge. And what are the other, what else in here can bond these things together? Well, these are hydrogen bonds, which are relatively strong. CO2 is a nonpolar molecule. London dispersion forces, very weak. Throw that one out. S8 is a symmetrical solid, but it still would require some heat to melt it, and phosphorus also. But what are the strongest bonds in here of all? For intermolecular interactions, the ionic bonds. Magnesium fluoride will be the very highest melting temperature of all of these. How about 16? Which of these statements is false? So either they're all true to satisfy E, or one of them is false to satisfy the statement as given. Diamond is a covalent crystal. Is that true? Yep. Every carbon is bonded to 4 other carbons with a covalent bond, and it forms a crystal network. In fact, one interpretation is that a perfect diamond with no flaws is a single molecule from edge to edge. B, the size of the unit cell of lithium and cesium is the same. Okay. Lithium is, well, they're both in the same family, right? They're both alkali metals, right? Here's lithium and there's cesium, okay? So their chemical behavior should be the same. But if you put them into a pure crystal lattice, the size of the unit cell cannot be different because cesium is a much, much bigger atom. It's huge. So the size of the unit cell would have to be smaller for lithium than it is for cesium. So B is false, definitely. And that may be the only one, which would make it the answer. The C, the molecular crystals usually have low melting points. Yeah, molecular crystals do, because they don't have covalent bonds to hold them together. So when you disrupt the crystal, if it's a molecular crystal, which would, for example, would be ice, as opposed to an ionic crystal or a covalent crystal. A molecular crystal is where you have individual molecules and they've been made to form a solid by cooling and compressing, and the bonds between them are relatively weak, actually. So that's true. Metallic crystals are usually good electrical conductors. Metallic crystals, that is where you have metal surrounded by its free-floating ions, that makes them good electrical conductors. Those electrons are free to move from one to the other. So really the only false one in here is B, right? They're not all true, so we can't be E. So B has to be the answer. 17. How would you expect the melting point of carbon tetrachloride to compare with that of sodium chloride? The melting point of sodium chloride would be very high. Takes very high temperature. Whereas carbon tetrachloride, in fact, at room temperature is a gas. Carbon tetrachloride. Hold on a second. It's a liquid, but it's very volatile. Okay, so how would you expect the melting points to compare? Should be lower because sodium chloride forms an extended ionic crystal, whereas it's covalently bonded small. When you're comparing carbon tetrachloride to sodium chloride, then it should be lower, means the value for carbon tetrachloride should be lower because. So sodium chloride forms an ionic crystal lattice, whereas carbon tetrachloride is covalently bonded small molecule. That's true. And we look and see we don't have any odd choices like none of the above or two of the above, or they're all false, or those types. In that case, all you have to do is run down. When you find the first true one, or the one that answers the question, you're done. Okay, and in the interest of time, we're going to move on. A is the answer to 17. 18. Which of the following is most likely to be a solid at room temperature? In that case, you want the one with the strongest intermolecular forces to be a solid at room temperature. So we look at water. We know that it's a liquid. Nitrogen's a gas. Ammonia is a gas. HF is a gas. The only solid one in there is the ionic compound, sodium sulfide. 19. At normal atmospheric pressure and a temperature of 0 degrees, right? 1 atmosphere and 0 degrees. Those are the conditions. Which phase of water can exist? All right. I know I've said this before, but I'll say it again. If you have solid water, ice, and liquid water, ice, together, and they're in equilibrium, so you've got both phases, and the water is pure, we haven't added anything to it, then you are at the freezing point of water, 0 degrees. So that being said, you have two phases present at this temperature and 1 atmosphere pressure. You have ice and water together. Now you can see that on a type of phase transition diagram. So there's your temperature, and this is progress from left to right. So if you start off as a solid, then you add heat by temperature until you get to all liquid. So in here, you can have solid and liquid. All liquid here. Right? So that's 0 degrees. Then when you get all liquid and no more solid left, you increase the temperature and you've got liquid, gas together. Solid, solid, liquid, 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 gas, until you get to here. And now you've got all gas. That's not right. Excuse me. That is as wrong as it can possibly be. What you have here is the solid only. You're heating up the solid. Ice. When you reach this point, now you have solid and liquid together. Solid and liquid together is stable at 0 degrees until all of the solid is gone. Now you got liquid only. You get to liquid and gas. Now when all the liquid is gone, you have gas only. And you can increase the temperature more. Okay? Anytime you have two phases together, the temperature is going to be fixed until one of them is gone. If you go in this direction, the liquid is gone, the solid is gone, now you got liquid. If you go in this direction and you're freezing it, then you reach a point where all the liquid is gone, and now you have solid, and you can continue to cool it down. What's happening in here is all of the energy that you add will not raise the temperature because it's being used to break the intermolecular forces between the liquid molecules, in the solid, excuse me, to make liquid. Okay, we're going to use that diagram again, so I'm going to leave it there. 20. Well, the answer then is A. 20. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made. I may have to erase that anyway, because I don't have a lot of space. So what are the conditions that were given? You're measuring vapor pressure. That means you have to have a liquid here and a gas here. And this has a lid on it. Otherwise, you won't develop any pressure. So we measure the vapor pressure up here. And what does that mean for number 20? Two processes, evaporation, right, going this direction, and what's that called? That's called condensation. Those two processes are going on at the same time at equal rates once you've reached equilibrium and the pressure is not changing anymore. And you haven't changed the temperature. Okay, so that's E is the answer. Let me say a word about terminology. If we have gas phase here, and we have liquid here, and we have solid here, okay, you could go from solid to liquid to gas. You know, that's one possibility. But there are names for each one of these. So if you go from solid to liquid, that's called melting. If you go from liquid to solid, that's called freezing. Those are common words. We know those. If you go from liquid to gas, that's called vaporization or boiling. Either one. If you go from gas to liquid, that's called condensation. Okay? If you go from gas to solid, that's called, well, let's go the other direction first. Solid to gas is called sublimation. And if you go from gas to solid, it's called deposition. Okay? Just so that the words mean something. Oh, okay. Fusion is a possibility for freezing. That's actually the proper term. Fusion. And melting is proper for that one. Okay. So now let's move on before I completely run out of time. I have a sneaking suspicion I'm going to run out of time anyway, so I'll just keep going. 21. There we go. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? Remember when we said when the intermolecular forces are increasing, all of those processes that we mentioned would also increase with increasing intermolecular forces. There was only one that would decrease. So if you increase the intermolecular forces, you decrease the vapor pressure. And how do we know the intermolecular forces? One indication is boiling point. If the boiling point is high, the intermolecular forces are high. So how would that affect the vapor pressure? Well, if you're looking for the highest vapor pressure, you want the lowest boiling point. Right? In that case, diethyl ether is the best one out of this bunch. In fact, if you pour diethyl ether out on your gloved hand, it would evaporate like that. Because what's normal body temperature? 37 degrees centigrade, Celsius. The boiling point is 34.5. It would go flash like that. Okay, 22. 22. Which one of the following decreases as the strength of the attractive intermolecular forces increase? Well, I've already answered that question, didn't I? The vapor pressure. You increase the strength of the forces in the liquid, you impede evaporation, which is an expression of vapor pressure. 23. In which of the following processes will energy be evolved as heat? All right, so let's do a picture. 23. So remember, when we have a system, if heat is evolved, if that's the direction of heat, heat is moving that direction, then our evolution of heat would give us a negative delta H. It's leaving the system. If we're adding energy in the form of heat, then we have a positive delta H. So what processes, when they occur, give up heat, go this direction? Well, sublimation is going from solid to gas. It absorbs heat. That can't be it. It's not evolving, it's absorbing. How about crystallization? Crystallization is like going from liquid to solid. That's also known as fusion. Crystallization, when atoms or molecules get closer together and bond, they give up energy. That's a lower energy state. So that would be the answer, crystallization. Vaporization, if it becomes a vapor, you've got to add energy, right? It can't be. Melting, if you're going from solid to liquid, you got to add energy. So the only one that fits is crystallization. 24. All right, we've got these liquids, 3 liquids, X, Y, and Z. Oh, 24, excuse me. There we go. 24. X, Y, and Z, how are they related? The normal boiling point of X is less than Y. Boiling point of X is less than Y, which is less than Z. I believe that's the trend. Yes. Okay. So if those boiling points are less, which is the correct order of increasing vapor pressure? The lowest boiling point will be the highest vapor pressure, right? So the vapor pressure should be the other way around. ZYX, which is B. Okay? Okay, let's see. I think we beat that horse enough. Let's move on to something else. Next page, 25. Okay, we're looking at a diagram here. And just so you know, pressure is on the abscissa, no, the ordinate, the y-axis, and temperature is on the x-axis, increasing from left to right, increasing here from bottom to top. And these are lines are there to divide the different phases. This is a phase diagram. And 1 atmosphere is marked here with this horizontal line. Okay, so the phase lines are here, here, and here. All right. Choose the statement, the correct statement below. So none of the statements could be correct. I mean, that's possible because E is one of your choices. But if one of them is correct, then of course E can't be right. So let's take them one at a time. The diagram is qualitatively correct for water. Okay, everything's in the right place, solid, liquid, gas. But what do we know about the boundary between solid and liquid for water? The slope of that line for water is not positive, but negative. It should go that direction. So A can't be right. How about B? The diagram shows that the melting point of the solid increases with increasing pressure. Okay, where's the melting point located? Between solid and liquid. So the melting point is along this line, and it varies with pressure on the positive slope. So as the pressure increases here, like this, pressure increases from here to here, what does T do? Well, if it's here, temperature is there. If the pressure increases to here, the temperature is here. So the temperature does increase on that line as the pressure increases. So B is true. Test-taking technique, we can stop right there. 26. Yep, we're going to look at 26 also. This phase diagram for compound Q. You wish to purify a sample of Q that was collected at 1 atmosphere and 100 K. All right, let me sketch this one out. 26. So we've got this, that, pressure here, temperature here. We've got, let's see, 200, 100, 300 K. Oops. Temperature in K. And pressure is in there, 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 there. And this is 1 atmosphere. This is a half. This is 1.5. This is 2. Okay, now for our diagram. It goes up to about here, right about there, from 0. Okay, then it continues on at almost the same slope, like that, and then like that. Okay, now this one starts at here and goes up to 1.5 at roughly here. Okay, so now we're told that the Q was collected at 1 atmosphere pressure and 100 K. So it would be right here. That's our starting point. In order to sublime the sample, what should you do? Well, we got 5 choices. Right, this is a solid, this is a liquid, this is a gas. So our sample is a solid, and we want to go from solid to gas directly. If we're going to purify it, that is sublime it, then we need to go from solid to gas. If we hold the pressure constant here and go that direction, we're going to make a liquid. That won't work. We need to go from solid to gas. So we either hold the pressure, we either hold the temperature and then drop the pressure, which would go solid to gas. Or we could drop the pressure down here and then go add some heat and go to gas. So let's see which ones work. Increase the pressure to 1.5 and then increase the temperature to 300. 1.5, go up to here, and then go to 300. No, that'll make a liquid. Won't work. B, increase temperature to 300 and keep the pressure at 1. That won't work either. That won't make a gas. It'll make a liquid first, and that defeats our purpose because we want to sublime. How about C? Lower the pressure to 0.5, come down to here, and then increase temperature to 200. That'll do it. Right? We found our answer. We can stop. Okay, 26. What's next? 26. 29. I'm going to switch to black. Let's see. There we go. Okay, 29. No, 26, 27, 28, 29. Here we go. Given the phase diagram below, which of the following statements is false? All right. So what do we notice about this one? We notice that solids here, liquids here, gases there, and the melting line between solid and liquid is negative. What does that remind you of? Water, right? Water is definitely that way. So which one of these is true? The solid has a higher density than the liquid. Well, if the solid has a higher density than the liquid, we would expect this slope to be positive. We know that water, the solid, is a lower density than the liquid. And we would expect this diagram to be similar to not similar to water in this case. So A would appear to be false. And that means E is wrong. But what about the others? I mean, that's the best answer I can give for A, but what about the others? At some constant temperature, right? So here, and then we would do something with the pressure, the gaseous substance can be compressed into a solid and then into a liquid, right? So at some constant temperature, you can compress from gas into solid and then liquid. That's true. If, say, we were right in here, we could go into solid and then liquid. B is true. When phase A, over here, is compressed at constant temperature, at point X, here, no change is observed. Is that true? Well, that dot there is supposed to signify that that is the critical temperature and pressure, the critical point. Beyond that point, anywhere in this region, you can't tell the difference between gas and liquid. There are no phase boundaries between the two. It's just a supercritical fluid. So if you did what they said to do here, increase the pressure, then you would never see a difference. You would never be able to see the change from gas to liquid. That's true. C is also true. Okay, when heated at 1 atmosphere from here, this substance will first melt, solid, liquid, and then boil. Yes, that is true. Follow that line across there, and you will reach the same conclusion. So really, A is still the only best answer. How about 30? The measure of resistance to the flow of a liquid is, this is definition, that's called viscosity, right? E. Let's see. We're getting there, slowly but surely. How about the next one? Now we're into moderately difficult questions. Number 1. So I should have marked that up here too. Those earlier ones were easy. This one's moderate. Moderate. And we're going to look at 1. Which of the following is the correct order of boiling points for KNO3, CH3OH, C2H6, and neon? All right, so this is medium 1. And what are our choices? KNO3, CH3OH, C2H6, and neon. Okay, when you have to put things in order like this, what I like to do is nail down the ends, right? What has, in this case, we're looking at boiling points. So we'll find out which one has the highest boiling point, which one has the lowest boiling point, and then we fit the others in the middle. So let's do that. So which one has the, let's see, in order of boiling points. So we're increasing from left to right. So the first one we want is the lowest boiling point. Which one would that be? Neon, obviously, right? It's not a compound, so the only forces it has available for bonding are London dispersion forces. But not only that, it's a single atom, so the expression of London dispersion forces is exceedingly weak, right? The larger the atom, the more opportunity you have for redistribution of electron density. And neon being pretty small, it's going to have the lowest boiling point. So neon first, right? And then at the other end, we want the highest boiling point. And that's going to be the ionic compound, if there is any. Right? There it is right there. KNO3. That would be over here. That's the highest boiling point. Now we've got that one, and we got this one. We just need to put these in order. So what's the difference here? This is methanol. It has, those are hydrogens. It has an opportunity for hydrogen bonding. Whereas this is ethane, which is a gas actually. And it's nonpolar, and it only has London dispersion forces, but they're a bit stronger than neon because you have it spread out more. So this should have a higher boiling point than that. So we should find CH3OH here, and then C2H6 there. So that's how you put them in order, logically speaking, which makes the correct answer D. All right, so that was 1. 2, which of the following statements is or are false? So it could be more than one of them false. Right. So let's see. 1, the layering in a hexagonal closest packing structure is ABA. So you have to think back to our discussion of what are the possible layerings. You got A, B, A layering, and then it starts over again with B again. Or you got A, B, C, and then you start over again. Let's see, A, B, A, C, A, or A, B, C, A, and then you just keep going like that. So what do we know about those? Well, you just have to remember. I mean, you have to memorize it. This ABA is actually hexagonal closest packing. Right? If you look at the unit cell in there, you find that it forms a hexagon. Whereas this one, I believe, was a face-centered cube. Okay, a body-centered cubic unit cell has 4 atoms per unit cell. Is that true? So 1 is true. 1 is true. How about 2? Body-centered cube. Okay, you're always going to have one here, 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 and here. Simple cubic. You could have one in the middle, body-centered, or you could have them on the face. So body-centered, we have one in the middle. Now, that one belongs to that cube, so there's one there. How many of the others belong to that cube? Well, each one of these has to be shared with 1, 2, 3. 1, 2, 3. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Has to be shared with 8. So there's 1/8 of each one of these that belongs to that cube. So we have 8 times an 1/8, and the total then is 2. So Roman numeral 2 is false. This one's true, this one's false. How about 3? We found one false one. For unit cells having the same edge length, a simple cubic structure would have a smaller density than a body-centered cube. Think about it. If they have the same edge length, they have the same volume, true? Right. So density is equal to mass divided by volume. If volume is fixed because of the edge length being the same for each of them, if you have 1 in here with a simple cube, then it's going to have 1 density. But if you can stick another atom in the center, then you've actually doubled the amount. And then the second one would be a greater density because it has more matter in that same volume. So 3 is true. And Roman numeral 4. Atoms in a solid consisting of only one element would have 6 nearest neighbors if the crystal structure were a simple cubic array. A simple cubic array means that you're missing this one. It's just like that. Okay? So atoms in the solid consisting of only one element, like this, would have 6 nearest neighbors. Perfect example. We talked about this earlier, sodium chloride. So if you have that one sitting there, you could have a cube here, 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 here. So the nearest neighbors, you could have a cube stacked up here, and its nearest neighbor would be there. Or it could be over here. Or it could be here in that crystal, or it could be out here, or it could be down there. So 1, 2, 3, 4, 5, 6. That's true. 6 nearest neighbors. Sodium chloride is an example of that. It's a simple cube. Its nearest neighbors are all chlorines or chlorides for sodium, and all sodiums for chlorides. So really the only one that's false is 2, is Roman numeral 2, which is B. 3. Which of the following substances would you expect to have the lowest boiling point? The lowest boiling point is the easiest to break intermolecular bonds. Any type of bond that can be broken easily is a low boiling point. Right? So the lowest would be, which are the strongest bonds? Well, take it from bottom to top. Copper has metallic bonding. That's reasonably strong. Diamond, it takes a lot to boil diamond because all of the network is covalent bonding. Very strong. Methane. Methane is a nonpolar symmetrical molecule with only possibility London dispersion forces. That's a candidate, right? CH4. Sodium nitrate, it's ionic, very high boiling point. Glycerin or glycerol, look at all these OHs. That means that hydrogen bonding is possible. Right? So it's going to be a higher boiling point than methane. Methane is really the lowest boiling point of all of those. 4. Okay, 4 takes some juggling. And let's see. What did I do with it? We're gonna, let's see, 2:30. And we're good till 3. Well, I've already accepted the inevitable. I'm gonna run out of time. So I'm just gonna keep talking and we'll just take them in order. It would be better if I could finish on time and then you'd have an opportunity to ask questions in real time. But que sera. Number 4. This is going to require some calculation. Say you start off, you have at your disposal 12,500 joules. So you have total energy available is 12,500 joules. Right? And you're going to add that to a sample of water as ice. So the moles of water is 2 moles, which it translates into 36 grams. You might need both of those. You're starting off with ice at 0 degrees. Okay, so your starting temperature is 0 degrees C, solid ice. All right. Now you're also given the molar heat of fusion. So the delta H fusion for ice is 6.02 kilojoules per mole. The specific heat, S, for water is 4.18 joules per gram degree C. And the molar heat of vaporization for that is 40.6 kilojoules per mole. Okay, that's everything that's given. The question is, what is in the resulting sample? Right? So your choices are, is there still ice, only ice? Is there ice and water? Is there only water? Is there water and water vapor, or is there only vapor? Right. So that goes back to our diagram. Right? Progress, temperature. Like that, 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 and that. So here we have 0 degrees. That's where we're starting, right here. Right there. Okay. So this is going to be only ice, solid. This is going to be solid and liquid. This is going to be liquid. This is going to be liquid and gas. This is going to be gas. So these values are given in such a way that heat of fusion is converting right here solid ice to liquid. This one's going to be heating the liquid, right? Specific heat. And this one's going to be here, converting liquid to gas. Okay. So what we have to do is we have to use it up in sequence. How much energy does it take to go from here to here? All solid to all liquid. Okay? So I'm going to have to erase some of this, so let me do that. Let's put that over here. 12,500 joules. So I can erase that. And we have 2 moles, or 36 grams. Okay, I can erase that. All right. How much energy does it take to melt that ice? Well, we've got this many kilojoules per mole, but we've got 2 moles. Right? So 6.02 kilojoules per mole times 2 moles means 12.04 kilojoules, which is 12,040. Joules. This says how much do we have left? 0, 6, 4. 460 joules. Okay? So now we have that much left, and we're at liquid. So we're going to heat the liquid up and see if we can make it to gas. So what happens here? Let's see. As we're going from 0 degrees to what? So what's the formula? Right. The heat required is actually it's expressed this way. Usually it's written as Q. Q equals S mass change in temperature, right? So how much heat do we have? 460 joules. S is 4.18. I'm going to leave the units out just for convenience. The mass is 36 grams. And what's delta T? It's the final temperature minus the initial temperature, which is 0. So now we have an equation in one unknown. Well, this is the final temperature. Right? So we take the final temperature and we divide both sides by this number, divide both sides by that number, and that'll tell us what our final temperature is. So 460, 4.18 divided into that, and 36 divided into that is 3.6 degrees. Actually, it's 3.3 3.1 degrees. All right, so what do you have? You got cold water, right? It's all water. It's still right in here. In fact, you're way down here, right about there. So it's all water, liquid water, nothing else. So that's the answer C, only water. Okay? That took a while, but it was important, I think. All right. So let's see, which one do I have marked off next? Oh, we're getting into difficult ones here. All right. Difficult number 1. All right. So now we're talking about number 1. Excuse me. Let's get down there. There we go. We're talking about firing X-rays at a crystal. And we're trying to find out something about the angle. So what are we talking about here? We're talking about the Bragg equation. Remember where the angle of the X-rays entering the crystal is fixed by the Bragg equation. Except that you can get several orders. You can get a first order, second order, third order, depending on the angle. Okay. So you need to look at your useful information. So you don't memorize the equation. It's right here. The Bragg equation is N, which is the order, times the wavelength. I can do better than that. Times the wavelength is equal to 2 times the distance times the angle. This is the distance between the lattices in the crystal. This is the wavelength of the light, and this is some arbitrary number. So let me get back over here to 1. No, not that one, this one. Okay. And I want to economize my time. Here we go. So, what are we given? Well, we're given, I'm going to use the hard copy so I don't have to turn around. We're given that the X-ray wavelength is equal to 2.33 angstroms. And the angle of the first order, the theta of the first order, where n equals 1, is 19.2 degrees. And the question is, what would the angle of the second order be? Okay? So let's think of this logically. What do we need to find this angle? Right? If that's the unknown, then we need this distance, that wavelength, and that order, don't we? Do we have that? Yes, that would be 2. Do we have this? Yes, that would be 2.33 angstroms. Yes. Okay. This distance between the two layers is the question. That's the one we don't know yet. So at this point, we have an equation in two unknowns. So we need simultaneous equations to solve it. But one way around that is to combine one equation into the other. Right? So if we say, what would the first equation look like? Well, the first one would be, for this one, would be 1 times the wavelength equals 2 times d times the sine of theta. And that's theta 1. Okay? The second one would be 2, same wavelength, 2, and then the distance would be the same for both of them. And then the sine theta for the second one, right? And that's the one we want. Okay, so can we combine those equations so that we can solve for this one? Well, what do they have in common? What they have in common is the two d's are equal. So if we solve this one for d, and then we solve this one for d and substitute and make those equal to one another, then perhaps we can solve for the theta. Oh, I missed something, didn't I? 19.2 degrees. All right, now we're getting somewhere. Okay, so why don't we solve this one for d and substitute it in here for that one? So this one would be d equals 2.33 divided by 2. All right, bring that 2 over here and bring that sine theta over here. Okay, then we take this whole thing, that's gone, 2 divided by 2, and put this one in here. So now this one becomes 2.33 divided by sine theta 2. Okay, now we have an equation in one unknown. All right, so I'm going to have to erase some things now. All right, so that 1 goes out, right? 1 multiplied, 1 divided, doesn't matter. So what we've got here is, let me write it out, 2.33 angstroms equals 2 times 2.33 angstroms divided by sine theta, second one, times sine of 19.2 degrees. Okay, so now we want to solve for this one. So all of these are multiplied or divided, so we don't have to worry about pluses or minuses. So we can take this one and put it over here, and take this one and put it over here, right? And that means that 2 times 2.33 over 2.33, that becomes 1, and this is sine 19.2 degrees. So now, this term is equal to that term, and all we need is the sine of 19.2 degrees times 2. So you have to know where it is on your calculator. 2 times, and that's 0.6577. 0.6577. Sine of that times 2. Now, how do we solve for theta 2? Well, you use the arc sign. The arc sign is kind of like the inverse, but it's not really. In other words, if we knew this one, then the sign of that number would be this. So we need a function on our calculator that'll go the other direction. If you know the sign, what's the angle it came from? So I've already got the sign in here. I just need to find the key that refers to arc sign. And in my calculator, it's a shift above sign. So the sign key is here. I hit the shift key, goes to arc sign, which takes this back to the angle. So I would say arc sign, which is 41 degrees. So theta is 41 degrees. And that would be, well, closest one is 41.1. Actually, if I carry it out to another decimal, yes, it's 41.1. Best answer is B. All right. I know that took a lot of action, and it required some algebra, right? Solving for one, substituting into the other one. And that's just the way that you solve two equations in two unknowns. If you remember your algebra, that's how you do it. Okay. All right, that was one. Let's see, what's coming next? 2. So let's do 2. Okay, we're going to be solving an equation here, trying to find a numerical answer. All right. Oops, it needs to be 2. Okay, for this one, chromium metal crystallizes as a body-centered cubic lattice. If the atomic radius of chromium is 1.25 angstroms, what is the density of chromium metal in grams per cubic centimeter? Okay, it's on the surface, it's a complex problem. We need to break it into pieces. And to do that, I say, what do we know first? All right, the chromium structure, the unit cell, is a body-centered cube. Okay, that's given. We know that the atomic radius of chromium is 1.25. So the radius of chromium is equal to 1.25 angstroms. Okay, and the question then is, what's the density of chromium? So we want to know the density of chromium in grams per cubic centimeters. That's what we know. That's the question. Now, do we have everything we need? Well, let's look at what's called for. Density. It's equal to mass divided by volume. The mass needs to be in grams, and the volume needs to be in cubic centimeters. Or milliliters, whichever the case may be. So we've got to find both of those terms out of this. All right, let's do mass first. What's the mass of chromium in the body-centered cube? Well, we need to know how many chromium atoms are in a body-centered cube. And we determined that earlier. It's 2. 2 atoms. So if we start off with 2 atoms, in the cube, we want to find out how much mass is that. Trying to solve for that. All right. So we need how many atoms in a mole? Right? Avogadro's number. Okay, that gets rid of atoms. Now we got mole. What else do we know? We know the molar mass of chromium because we have a periodic table. Chromium's right here. It's 52.00 rounded off. So this would be grams per cube. So now we know the mass in that unit cell. All we have to do is solve for it. Right? So let's do that real quick. So we have 2 atoms. We have 6.02 times 10 to the 23rd divided into it, right? Divided in, and then multiplied by 52. So that's 1.728. I'm going to hang on to a few decimal places. 1.728 times 10 to the minus 22. Is that right? Yep. 1.728 times 10 to the 22 grams. Negative 22. Now we got the mass. Okay? Now we need the volume. So how do we calculate the volume? I'm going to have to erase this for now. So what's the volume of a body-centered cube? Go to your useful information. It's given. The formula for a body-centered cube is, well, the edge on the cube is 4r divided by square root of 3. And this is the one edge of the cube, right? So the volume would just be, once we find that edge, would just be a cubed, right? Because the volume of a cube is one side cubed. So the radius then we know is 1.25 angstroms. Right? So if we substitute 1.25 angstroms, we should get the edge of that cube. What did I do? Here it is. So 1.25 times 4 divided by the square root of 3 is 2.887 angstroms. 2.887 angstroms. But we need cubic centimeters. So let's change that to centimeters first. How about that? .887 angstroms, and we want to change that to centimeters before we cube it. So what's the ratio? Well, angstrom related to meters is 10 to the minus 10th meters. Okay, so we got angstroms there. Now we convert that to centimeters. There we go. Now, so we can do that in our head, right? 10 to the minus 10th and 2 means this is 10 to the minus 8th centimeters. So it's 2.887 times 10 to the minus 8 centimeters cubed is the volume. So we got mass divided by volume. You just divide this one by that one, and you've got your density. So let's see, am I still in there? Yeah, still in there. So I need to change this one to 10 to the minus 8th. Right? And then I need to cube it. So let's see. Okay, so I get 2.506 times 10 to the minus 23rd cubic centimeters. Divide that into those grams. And I get 7.18. Let's see, is that correct? How am I limited on significant figures? 1.25 angstroms, so 3 significant figures. 7.18 grams per cubic centimeter. Let's see, did I even get close? Yeah, B, 7.18. Okay, I know that took a lot of work, but it's good exercise for your brain to work these types of problems. Let's see, I don't have any more in this chapter. So now we can go to chapter 11, and I'm out of time. So I'll just keep going. If you have to leave, then so be it. But I'm going to cover chapter 11 now. Let me get this one out of the way. So I need to stop this share and go to the review document for chapter 11 and share it right here. There we go. Yes, that's chapter 11. Okay, so let's erase this stuff. You know what? I want to start with a fresh board. I'm going to clean this one off. It just take a second. Yeah, that's better. Not perfect, but it's better. Okay. Now we're into chapter 11. In my textbook. Here we go. Chapter 11. And we're going to do the whole first page. Here we go. So, number 1. And this is the easy section. Um, 0.1 molar solution of sodium chloride. That's what we're given. Okay. And the question is, which one of the following will be closest to 0.1? Is it 0.1 mole fraction? 0.1 mass fraction? 0.1 mass percent? 0.1 molality? Or are all of them 0.1? So what would be the mole fraction for 0.1 molar sodium chloride? That's A. Well, 0.1 molar is moles per liter. And we want to convert that to mole fraction. So what we need is how many moles is that relative to moles of water? Let's see. How did I approach this before? In the interest of saving time. Okay. Mole fraction then, where we're headed with mole fraction is moles of sodium chloride per total moles of solution. Okay. So in let's change this to mass. Moles of sodium chloride per gram of solution. Okay. So this would be liters per 1,000 milliliters. Right. And then we know that pure water is about 1 gram per milliliter. So we're saying that this is a dilute solution. It's dilute enough to give us an estimate. Okay. So that value would be 0.1 divided by 10 to the third, 0.1 times 10 to the third, 10 to the minus third, would be 1 times 10 to the minus fourth. Oh, excuse me. No, it's 0.1 mole per 1,000 grams. Right, 1.1 and 1,000. Okay, so that would be 0.12 that. Right, 1, 2. No. All right. So this is moles per gram. Okay. So gram of solution if we assume that the sodium chloride is so dilute that it has no influence on the moles of solution. In other words, we can treat it as if it were pure water. So this is kind of a iffy situation. Grams of water would be 18.02 grams per mole of water. So, and we're saying this is moles of solution. So 18.02 times this would be 1, 2, 3, 4. So we go 1, 2, 3, 4, 0, 0. So mole fraction would be, okay, so A, its mole fraction would be 0.0018. 0018. That's nowhere near. That's nowhere near the value of 0.1. Way off. So let's look at B. All right, so B is mass fraction of sodium chloride. So that's grams of sodium chloride per grams of solution. So 0.1 moles per liter. Is that where we want to start? Yeah, liters fine. Liters of solution. Let's see. It's getting hard to write on this thing. Let me see if I can get some of that oil off. There. So what we want is grams. If it's mass fraction, it's grams of sodium chloride per gram of solution. So we need to change all right, so let's say this is equivalent to water. So this would be grams of solution, well, actually milliliters of solution would be 10 to the third per liter. Right? And then if we said 1:1 milliliters per gram, close enough. So now we've got grams of solution. Now we need grams of sodium chloride, right? So 0.1 mole, for 1 mole sodium chloride, the molar mass is 5844. So now we have grams of sodium chloride per gram of solution. That's what we want. So it's 0.1 and 1,000 and 1 and then 58.44 times. So I get 5.8 times 10 to the minus third. So the gram fraction mass is 5.8 times 10 to the minus third. There we go. That doesn't work either. What's C? C is mass percent. Right? If this is mass fraction, then mass percent is just 100 times that. Because this is parts per 1, we need parts per 100, which would be 100 times. Which would be 10 to the first, which would be 58, which is 58%. Right? So that value is nowhere near 0.1. How about the molality of sodium chloride? Molality is, we go from 0.1 mole per liter of solution, but we need mass of solvent. So 0.1 mole of sodium chloride is 1/10 of its molar mass, right? So that'd be 5.844. Per liter. Excuse me, grams per liter. Okay, so what's the mass? Well, we sort of have to assume that 1 liter of solution would be 1 kilogram, but we have to subtract out the kilograms of this one. So actually we're saying 1 kilogram. Let's say that's not right. we still want moles. We still want 0.1 moles. But the mass now is 1 liter is 1 kilogram minus 5.844 grams, which would be 0.005844 kilograms total. So we don't even have to calculate. This is going to be such a small number that this is going to essentially be the same as molarity. Molality for this solution is almost identical to molarity. So that's why D is the answer. And it took me forever to answer that one, but I figured the procedure was worth the effort. How about 2? Which of the following concentration measures will change in value as the temperature of a solution changes? Remember, the volume of a solution changes with temperature. So any one that has volume in its measure will change. Mass percent, no, only mass. Mole fraction, nope, no volume there. Molality, nope, I mean only moles and mass, won't change. Molarity, that's the one. Molarity changes because it's moles per liter, and the volume is liters, will change with temperature. All right. 3. Which of the following chemical or physical changes is an endothermic process? Endothermic. You have to add energy, any heat, to do the process. Evaporation of water. That's definitely endothermic. Combustion of gas. That gives off a lot of heat. That's exothermic. Mix sulfuric acid and water. Believe me, that will get very hot. Freezing water. As water freezes, the water itself, the system, decreases in energy. It's got to give it up somewhere. It's exothermic. So the only one that fits this scenario is A. Evaporation of water is an endothermic process. 4. Which statement about hydrogen bonding, is true? Okay. Hydrogen bonding is the intermolecular attractive forces between 2 hydrogen atoms in a solution. False. We already looked at that one earlier. Hydrogen bonding capabilities of water molecules cause CH3, CH2, CH2, CH3. That's butane. To be more soluble in water than CH3OH. No. The hydrogen bonding potential of CH3OH is much higher. There are no hydrogen bonds here, but methanol has opportunities galore to make a hydrogen bond with water. It should be more soluble than butane. Hydrogen bonding of solvent molecules with a solute will not affect the solubility. That's false on its face. If you've got hydrogen bonding capabilities, an increase in hydrogen bonding or the availability will increase the solubility of the solute because the forces of attraction are much stronger than for other types of polar interactions. Hydrogen bonding interactions between molecules are stronger than the covalent bond within the molecule. That's false. Covalent bonds are the strongest, and they hold molecules together so that they can act as single units. Hydrogen bonding arises from the dipole moment created by an unequal sharing of electrons within certain covalent bonds within a molecule. That's as true as you can get without adding any more detail. So E is the answer to 4. 5. Which of the following favors the solubility of an ionic solid in a liquid solvent? How about A, a large magnitude of the solvation energy of the ions? Okay, what do we mean by solvation energy? The solvation energy refers to the amount of energy that is given up when the solvent and the solute attract. Solvation energy. When they come together, we've already made the holes and separated the solute. So now, if there's a large solvent energy, they come together, then that should favor solubility. That's true. The stronger the attraction, the more likely they are to form a solution. A small magnitude of the lattice energy of the solute. So what's the lattice energy of the solute? Well, lattice energy references a solid formation. Lattice energy. When you go from something that's a gas to something that's a solid, free gas atoms to the solid, then you give up energy. It's exothermic. So what does that mean? If it gives up energy going this way, then if it's going back to make the individual atoms so that they can go into the solution, and it only takes a little bit of energy to break them apart, that's good. If you don't have to put a lot of energy into it, then you have individual atoms or molecules ready to go into solution. That's a positive for the formation of the solution. B is true. A large polarity of the solvent. Well, let's look back at the ionic solid, right? The ionic solid is pulled apart here. Then the large polarity of the solvent will form the attractive forces. And that's just another way of saying A, the solvation energy is high. So all of these are true. They favor the solubility of an ionic solid in a liquid solvent. All right, let's see, what's the next one? Oh, it looks like I'm doing just about every one of them here for a little while. 6. This one takes a little math. Six. You have solid potassium fluoride right here with this data. We'll cover that in a minute. And you have solid rubidium fluoride. So rubidium and potassium are in the same group. Potassium's above, rubidium is the next one below. And the information we're giving here is used to determine which one forms the stronger attractions with water, right? Which one, in the process of going into solution, which one actually bonds more strongly with the water molecules. Okay, so let's see, here we go. What do we know? All right. So for the KF, we're saying here, let's see, lattice energy for KF is minus 804 kilojoules per mole. So for KF, the lattice energy would be going from gas, individual gases, to the solid Kf. And that last lattice energy is negative 804 kilojoules per mole. Okay? So when it goes from here to there, it gives up that much energy. So to go back the other way, you would have to supply that energy. Let's see. Similarly, for rubidium, to do that, it only gives up this much kilojoules per mole. Okay, this is the lattice energy. What else are we given? Let's see. We're given the heat of solution. So this is the overall value. The heat of solution for this one, see here, delta H of solution is equal to minus 15. And the heat of solution for rubidium is minus 24. Okay, that's everything that's given. The question is, which forms the stronger attraction with water? All right. So remember our discussion in the lecture on chapter 11, where we said the heat of solution, where the formation process of a solution, which is expressed as the heat of solution, can be broken down into three parts. Right? One is you break up the solid. Right? So this is the delta H1, where you break up the solid. The second part, delta H2, is where you separate the solvent molecules to make room. You break up their energy, holding them together. And then the third one is the attraction of the solute and solvent molecules to one another. That's what we're getting at here. Which has the stronger attraction for water? That's the one we want right there. So out of all this information that we're given, where do these fit? Well, this one fits, these two fit here. Okay? This one is energy required to break up the solid. This is the energy you get back when the solid forms. So to break up the solid, you would have to add that back. So we need to take this and change the sign. So this would be the lattice energy. Negative lattice energy because we're going the other direction. Right? So we have this one, we have this one. We want to get this one, but what's this one? This one is the one that pulls the water molecules apart. Well, it's the same for both, right? There's no difference of this one from this process and that process. So we can actually say, if we can solve for that term, then we know the difference is due to this term. See what I mean? Okay. So unfortunately now I'm going to have to erase some of this to fill in that. Fortunately, I've got my answer sheet here, so I don't have to remember the numbers. Okay, So how about the delta H, let's say for KF? The delta H for the KF, excuse me, is minus 15 kilojoules per mole, and that's equal to negative lattice energy. So the lattice energy is 804, and then plus this. Okay, this one, rubidium fluoride, then would be minus 24 kilojoules per mole. And this is a negative of that negative, which is 768. Plus the delta H. This is for KF, and this is for rubidium. Okay, so now we just need to solve for these two terms. And if we do, we find that delta H for the KF is equal to minus 819 kilojoules per mole. And the delta H for the rubidium fluoride is minus 792 kilojoules per mole. Right, so how does that answer the question? Relative to the system, as these things come together, the water and the KF, or the water and the rubidium fluoride, the stronger the attraction, the more energy is released, which means the negative number is greater. So the larger the negative number, the stronger that attraction. So the strength of attraction is greater for KF than it is for rubidium fluoride. Okay, I know it took a long time to get there, but we answered the question. Okay, let's see, 7, got it on my list too. Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the question below. So what do we got here? Well, we've got a gas that's being dissolving in a liquid, right? We're talking about Henry's law. So what happens? As you increase the pressure, you should get more gas dissolved in the liquid. That's why pop does what it does when you open the cap. It pops because there's pressure built up in there. But as long as you've got the cap sealed on your pop bottle, then the gas that's in solution stays there. It only comes out when you release the pressure. Okay, so let's look at our problem here. Which of the following statements are true? When the piston is pushed down. When the piston is pushed down, we expect for more gas to go into solution. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. No, cause the concentration of the dissolved gas to increase. This will cause the pressure of the gas to decrease and the concentration to go down. A and B are both false. C says this will cause the pressure of the gas to increase, yes, and the concentration of the dissolved gas to go up, yes. Now, initially, the pressure of the gas goes up as you decrease the volume, right? That's Boyle's law. But Le Chatelier says there has to be a response to that disturbance of equilibrium. And that response is more gas is dissolved in the liquid. And that explains Henry's law. So that's it. We answered it. We can stop there. 8. Which of the following correctly states the relationship between temperature and solubility of a substance in water? Okay. Normally, for solids in water, solubility goes up as temperature increases, but occasionally it goes down as temperature increases. For gases, though, the solubility of a gas decreases as the temperature increases. It's just the opposite. So let's see if that helps us with our statements. The solubility of a substance in water increases as the temperature rises, especially for gases. No, gases are the other way. The solubility of a substance in water decreases as the temperature rises, especially for ionic solids. Most of the time, that's false. So that's not the best answer either. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That's true. We can't say that it's soluble, more soluble or less soluble. We can say that, yeah, most of the time, but we cannot predict it for ionic solids. So C is true. How about D? Solubility of a substance in water decreases as the temperature lowers, especially for gases. Actually, as the temperature decreases, the solubility of gases increase. So that one's false also. So really, the only one that works is C. All right, let's see how we're doing here. Skip down to 10. Okay, a solution a solution contains 1 mole of liquid A and 3 moles of liquid B. Okay, this solution has a vapor pressure of 314 torr. What's a torr? It's a millimeter of mercury. 314 millimeters of mercury is the same thing at 25 degrees C. So it looks like temperature's held constant. At 25 degrees C, liquid A has a vapor pressure of 265 and liquid B has a vapor pressure of 355. What does that say? That says that we're using not Rayleigh law, but the modified Rayleigh law, in which both components are volatile, right? They both have an influence on the vapor pressure. So that means that the total pressure has to be taken into account for pressure A and pressure B. And this is also expressed as, let me see, my mind's tripping this time of day. B is the mole fraction of A, that okay. So we're still on 10, yeah. So what's the total? The total we're given is 314 torr. All right. So what would we expect? If this were an ideal mixture of gases, then that value plus that value would equal that value. They'd be equivalent numerically. But what so often happens is the solutions are not ideal when they're mixed together. So the summation of this could be bigger than that, or it could be less than that. If it's less, we have a negative deviation. If it's greater, we have a positive deviation. So what are the values? Liquid A has a vapor pressure of 265 and liquid B, and these are actual vapor pressures measured in the mixture, right? We don't have to do any calculation. So this one is, A is 265 torr, and this one's 355. So add them together, and you get 0, and then 11, 12, and then 1 is 6. So what do we have? A positive deviation from the ideal. No, excuse me. Negative deviation. This is what we would expect when you add the two together. But it's actually that. So we have a negative deviation. So there we have, this solution exhibits a negative deviation from Rayleigh's law. That's it. That's the answer. Now, if we look at the causes, we find that when you mix those two together, the intermolecular forces within this one, pure, and the intermolecular forces pure here are less than, either of them are less than pure than the combined. So they have an attraction for one another, which depresses the volatility and gives you a lower value for the total vapor pressure. Okay, let's see, what's next? 12. A cucumber is placed in a concentrated salt solution. So you got a cucumber, there's some seeds, and you put it in a concentrated salt solution. Just say sodium chloride solution. Okay. And this is concentrated. Very high sodium chloride solution. Concentration. All right, so what are we talking about here? We're talking about a colligative property. Osmotic pressure. And the semi-permeable membrane is where? It's right there. Each cell has a semi-permeable membrane surrounding it in this cucumber. So that's what's reacting with the concentrated salt solution. Now, what's going to happen? Generally speaking, a concentrated sodium chloride solution is much more concentrated in salt than inside the cell. Another way of saying that is there's more water in the cells than there is outside. So which way is the water moving? Because it's the only thing that can move. It goes out of the cell, correct? So if the water moves out of the cells, the cucumber should shrink in size and mass. Water will flow from the cucumber to the solution. That's it. Because the only other options are not right. No change will occur? Oh yeah, it will. Salt will precipitate out? No, it's just concentrated, it's not saturated. Salt will flow into the cucumber? No, it's a semi-permeable membrane. Salt can't cross the boundaries. Only water can. So it's either A or B, and B is wrong. Salt will not flow into the cucumber. It flows out because of the way that it behaves against the membrane. If you've got pure water over here, and you got sodium chloride over here, then you have fewer sodium chloride molecules here and more here going that direction. Okay? The osmotic pressure then is in this direction. Okay, 13. Osmotic pressure depends on all but which of the following? Well, let's take the formula for osmotic pressure. Right, so that one, and then we need molarity, right? And we need the gas constant, and we need temperature. But we also need our correction factor, the Van Hoff number. Okay, so now let's look at this and say, which one of these is true? Osmotic pressure depends on all but which of the following? Well, let's start from the bottom. The ratio of moles of solute to solution volume. Right there, molarity. That's true. Temperature. There it is. That's true. Molarity of the solution, that's another way of saying D. B and D are identical. Atmospheric pressure. Is there any place in there that has pressure? No. So A is the one that doesn't fit. Okay. Let's see. What's next on my list? 14. Okay. 14 is the last easy one. Shaving cream is an example of which colloid type? You just have to remember this one. Right. Shaving cream is what? Well, let's look at our possibilities. E, we do have E. Coagulate. Sol. Emulsion. Foam. And aerosol. Okay. Now, what are we talking about here? Well, we're talking about a colloid. We're not talking about a solution. Colloids are not solutions. Colloids are dependent upon the particle size of the solute. If the solute is small enough in particle size, the kinetic energy of the molecules in the solvent are sufficient to maintain the solute in suspended form. It's a suspension, but it's a stable suspension as long as we don't change anything. So what's an aerosol? Aerosol is a liquid or solid in a gas. So these are the solvents right here. This one is a gas in a liquid. Emulsion is a solid in a liquid. A sol is a, no, excuse me. Emulsion is a liquid in a liquid. And a sol is a solid in a liquid. And a coagulate is not a colloid. Coagulate is what a colloid does when you disrupt it and destroy its nature as a colloid. So what was the question again? Shaving cream. So what's in a shaving cream? Well, you have suspended gas particles, right? So it can only be this one, right? Out of those choices, a gas in a liquid is shaving cream. Now, some of those shaving creams start out as a gel, right? They're liquids in liquids. Well, an emulsion, but they're advertised as a gel, but they're emulsions. But the thing is, once you release the pressure on them, then the suspended liquid turns into a gas. And that's what makes the gel foam, expands. Two things. You're releasing pressure, plus you're spreading it on your skin, which is hot. And it increases the vapor pressure of the solute. Okay? And they pick things, just read a label. And they pick things like isopentane or isohexane, which have boiling points that are almost but not quite at body temperature. So when you hit them, when you hit your body with them, you have just enough heat to turn them into gas slowly. I mean, you don't want them to flash. It's a controlled recipe question. All right, so that was the last easy one. Now we're to moderates, and we're down to number 3 on moderates. Number 3, here we go. Moderates. All right. 0.2 molar solution of solute, X, in benzene displays an osmotic pressure given by this formula. Which of the following is most likely to be the case? All right, so we look at our answers. And it looks like what they're doing is they're referencing dissociation. You know, what contributed to that I correction factor. So if this is the formula that it's responsive to, 0.1 RT, and the 0.2 molar solution of the solute, X, 0.2 molar X. Right. Now, look at what we've got here. What would this formula be if it had no substitutions of actual numbers? It would be osmotic pressure equals molarity times gas constant times temperature. And with an I in there. So this term is actually IM. Okay? But if the solution is 0.2, this would be 0.2. How do you get 0.2 to 0.1? I has to be 0.5. So in reality, what's happening when you dissolve things in your solution, you actually have to start forming associations with the solute in solution. It has to pair to give you that reduced value. So let's look at our answers. X exists in benzene as, okay, so, okay, benzene is the solvent, right? X exists in benzene as X. If that were true, then this would be 1, right? And that would be, well, that would be the same value. It can't be. It won't work. X exists in benzene as X2. So there we're saying X, when it goes into solution, forms a dimer of some kind. That's the one that answers the question. Because instead of breaking apart into 2 particles, it combines from 1 into 2. So there's your answer. Next one is 4. All right. Which of these solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molal calcium chloride, would have higher vapor pressure and lower boiling point? All right. If we're going to talk about vapor pressure, we need molarity. Talk about boiling point, yes, molality works. But these are dilute solutions. So we learned in one previous problem that they're virtually equivalent. 0.1 molal is 0.1 molar, more or less. So what do we say? Well, let's see. What's going to happen when they, let's see. We need to know we need to associate each of these to its particle concentration. So what's the molality of sodium chloride in solution? Right? Because the particle concentration is what determines the vapor pressure or determines the boiling point. Right? So if we have more particles in solution, the first one is Raoult's law, pure, right, with a non-volatile solute. Right? So if we can say, if we can compare the particle concentration in each one, then we can say something about each. So for 0.1 molar sodium chloride, or molal sodium chloride, what's the particle concentration? That yields 0.2 molal. 0.15 glucose is the same. It does not dissociate. Calcium chloride (0.3 molal). Okay, so what do we know? If the concentration increases, then the vapor pressure decreases, right? Because we're changing the mole fraction of the solvent, which is responsible for the vapor pressure. So if we increase any of these, then the vapor pressure is going to go down. So the highest vapor pressure will be the lowest concentration. Here, glucose. So glucose is the vapor pressure answer, and the boiling point would be the highest, let's see, the lowest boiling point, excuse me. The lowest boiling point means the lowest concentration of particles, which is also, so the glucose concentration, it answers 1 and 2 both. Highest vapor pressure, lowest boiling point. All right, so let's see, we ought to be, and we got one more here, 5. All right, we're going to take the same information for number 5. And answer different questions. Which one, well, which one has the lowest boiling point, right? So that would have been, lowest boiling point will be the same, right? It'll be 0.15 molal glucose. But instead of the highest vapor pressure, 5 says the lowest vapor pressure. So the lowest vapor pressure is the one with the highest concentration of particles. And the highest concentration of particles is calcium chloride. So the calcium chloride is the first one, and glucose is still the second one. All right, now let's go to difficult. What number? Number 2. All right. There we go. All right, number 2. Let's read this one backwards. What is the molar mass of the solute? We got to find molar mass. Molar mass, I often say molecular weight. Same thing. We need the mass of a certain number of moles of the solute. Okay, that'll answer our question. So what are we given? A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute. That's the solute we're trying to determine is its molar mass, and 85 grams of water. So we've got 53.8 grams of the solute and 85 grams of water. Okay, we're given that. Now we're given the vapor pressure of the solution at 60 degrees is 132 torr. So the solution gives us 132 torr at 60 degrees. The vapor pressure of the water at 60 degrees, though, is 150 torr. What's the molar mass? All right. So, do we have anything already given to us that can fit into that formula? We got the mass of the solute, right? So now all we need to do is find the moles of the solute. How many moles of solute are we talking about? Well, if this solution is composed of this much water, and we know that its pressure, pure water is this, and its pressure in solution is this, we know the mole fraction of water because the solute is not volatile. So the mole fraction of water is proportional to 132 over 150. And that's equal to 0.880. Mole fraction of water. So we know that. All right. How many moles of water do we have? We got this many grams, right? So grams per mole is 18.02 equals 85 divided by 18.02 is 4.717. 4.717 moles of water. Okay? Now we're getting somewhere. Let me see if that's right. 132, 150. Yeah, okay. Now, I'm going to have to erase some things. 53.8 grams. Right, okay, so I got that one. I've used these already. Oops. I erased something important. 4.717 moles. 4.717 moles of water. There we go. Now, and mole fraction is 0.880. Mole fraction of water equals 0.880. Okay, so what does mole fraction mean? It means that's the fraction of water that's in solution. So the moles of water per moles of water plus moles of solute. Right? Now we're getting there. We need to know what this is right here. So how many moles of water are there? Well, the mole fraction is also equal to 0.880. We know what this is. We just calculated it. 4.717, 4.717. So now we have an equation in one unknown. This one is, let's see. Yeah. We take this term times that side. Right? So 4.717 times this is 4.151. 4.151 plus 0.880 times the moles of the solute. Okay? That's this times that. And leaves us with this on this side. Okay? Equal to that. But we want to put this back on this side. So this is now a negative on this side, which means 0.880 is 0.12. 0.120 equals 4.151. Everybody follow me? Okay, I'm just solving an algebraic equation. We have to take this term, multiply it by that, leave this one over here on this side. But now that that's over here, then we take this one and subtract it from both sides. Subtract it from 1 leaves us 0.12. So now the moles, no, that's solute, excuse me. Whoa. That's not right. That's a mistake. Hold on a second. Moles of water. Oh, we already got that one. 4.717, sorry, equals 4.151 plus 0.880 moles of solid. Okay. I apologize. Now, this is this value here. This one times that one leaves this one on this side right here. And this one times that one leaves this and that. So now I can take this one, 151, and subtract it from this side. 4.717 minus 4.151 yields 0.566. 0.566 is from here, combining with that one, and that leaves that equal to 0.880 moles of solute. So now we say this is equal to that divided by this one. Now we have 0.632, 0.632. Okay, so now we can calculate the molar mass and that was running out of steam. We got the mass divided by the moles. 0.632. So that should be equal to 83.6 grams per mole. Is that one of the answers? Let's see. Oh, I'm sorry, I didn't scroll down. There it is. Number 2. 83.6, is that one of them? Yeah, E. Okay, so that answers the question. Now, why is that important? Because this is a colligative property that we're dealing with, and it doesn't matter what the solute is. It only matters how much of it is there. So we can determine the molar mass of our solute independent of knowledge of its formula. And remember, in first semester chemistry, you should have learned how to determine the empirical formula from percentage composition. But then you go from percentage composition, from empirical formula to molecular formula only if you have an independent determination of the molar mass of the compound. And that's one of the ways that you can do it. All right, so that was 2. How about 4? Let's see, how many more we got? That's it. This is the last one. And I'm already an hour over, but looks like it's just me now. So I'll take my time and work this one out. Number 4. There we go. Number 4. Okay. Let's read number 4. You were given 10.40 gram mixture of sugar and salt. So sucrose and sodium chloride together weigh 10.4 grams. So we don't know what the composition is. We just know that the total is 10.4 grams. When the mixture is dissolved in 150 grams of water, the freezing point of the water is found to be minus 2.24 degrees C. What's the percentage by mass of sugar in the original mixture? All right. So in order to answer this one, we have to use freezing point depression. All right. So what are we given? We're given 10.4 grams of mixture. We're also given 150 grams of water. As the solvent, right? So we know we're going to have to use the colligative property of freezing point depression. And the concentration needs to be expressed in terms of mass of the solvent in kilograms. So that would be equal to 0.150 kilograms. Okay. Now, what's the freezing point depression constant for water? That's not given. Well, let's look. Should be in useful information, should it? Let's see here. Yes, at the bottom of the page, and the third column from the left, the freezing point depression constant for water is 1.86. So the K is 1.86 degrees C per, is that right? Degrees C kilogram per mole. Now, why did I write it that way? One way to write it would be degrees C per molal. But what are we looking for? Well, maybe we're looking for it and maybe we're not. But this is the same thing as divided by molality, because if this comes into the denominator, it's part of the denominator of this, and that becomes molal. So it's also equal to degrees C per molal, either way. Okay. Well, we're still looking at what's given. What's the change in temperature? The change in temperature for freezing point is 2.24 degrees centigrade. It has to be negative, right? The change of temperature is what we're dealing with. Delta T is 2.24 degrees C. Okay. Now, this is also equal to KFI molality. So we need our Van Hoff correction. Why do we know we need the Van Hoff correction? Because, well, it's not shown here. Because sucrose does not dissociate, but sodium chloride does. So the Van Hoff correction factor for sodium chloride is 2. You get 2 ions for every 1 unit of sodium chloride. Okay, we're going to need to know the molar mass of each of the compounds, right? Because there's moles in here as part of the answer. So I've calculated those. Sodium chloride is 5844 grams per mole. And sucrose is a lot bigger, 342 grams per mole. All right. So now, here comes the thinking part. We need algebra. Unknown city. Let X equal something. Let X equals the mass of sucrose. Now, why did we pick sucrose? Because the question asks for percent composition in the original mixture of sucrose. So we want to find out what this is. We know what the total is. If we can find this, then we ratio it to that times 100, and we have our answer. So we're solving for a component in that calculation. That's why we let X equal sucrose. So that means 10.4, and actually there's a 0 in here, minus X equals the mass of sodium chloride. All right. Okay, here's another important point. This delta T is also a summation of the effect on the freezing point of sucrose plus the effect of on the freezing point of sodium chloride. They're additive. So this is actually equal to the delta T for sucrose plus the delta T for sodium chloride. Okay, that's important. All right, So now we have all this information. We can write the expression for this total in terms of these values, and each one of these will have the expression for the freezing point depression. So we're going to expand this right? Expand this equal to that value, right? So now I've got to erase some things. Let's see. Yeah, let's go up here like this. I might be able to leave that for a little while. So 2.24 degrees. That's not behaving. I'm going to have to get a fresh one. 2.24 degrees is equal to the delta T of sucrose, which is the I factor for sucrose is 1 times the molality of the sucrose times 1.86. So what's the molality? Well, it's moles of sucrose divided by 0.15. Correct? That's the delta T for sucrose. This is the delta T there you go. So now, if we solve this equation so that we get all of these multipliers, well, on one side or the other. So we can take, this one is common to both, this one is common to both. But these two are different. So we can take this factor and this factor together, put them over here. 0.15, because it was in the denominator over here, and this one's in the numerator, 1.86. And that together is 0.1806. So all that is equal to now 1 times the mole of sucrose plus 2 times the moles of sodium chloride. All right. With me so far? Now, what do we know about the moles of sucrose and the moles of sodium chloride? Well, we have an expression for the mass of each one. The mass of sucrose is X. So the moles, if we use dimensional analysis, and we say that the moles of sucrose times the 1 mole per 342.3 grams. Then we know that if this is equal to the moles, then actually what we want to do is convert mass. So actually it's upside down, excuse me. Where's my, here it is. I got that wrong. We want to be able to substitute in for this value, moles of sucrose. So if we have a mass of sucrose and we multiply it by grams per mole, 2.3. Then we have the moles of sucrose. Okay, so now we can substitute this in here. And similarly, we can do that for sodium chloride. All right. So now what we have is 0.1806 equals, substitute in for that, which is X divided by 342.3. And then for this, 2 times 10.4 minus X divided by 58.44. Okay? So now all the thinking is done. We have an equation in one unknown, X. X will give us the mass of sucrose, and we can ratio the mass of sucrose to the total times 100. We have our answer. So what does X turn out to be? Let's see. If we do our algebra, X is, oops, looking at the wrong one. X turns out to be 5.60 grams. Okay, then divide that by 10.40 times 100, and you get 53.8% sucrose. All right. Okay, that's it for the review. That's everything. Let's see. Yep. There's nothing left. So we're done with the review. Check it out closely, and you should be ready for the exam. Between now and next Friday, anytime you want to take it. It's in Blackboard. You just have to be sure to go through Lockdown Browser. And when you start Lockdown Browser for the first time, unless you install it today, if you installed it in the past, then it will probably do an update to the program automatically. If it doesn't, then once it's loaded up, look for the check for updates and be sure it's updated. Then you can use that browser to go to Blackboard and find the exam. You should have access to useful information. I would suggest the first time we do this that you go in before you open Lockdown Browser, get useful information and print it out, because it's legal for you to have that plus the periodic table. So have those two with you, and that's kosher. You can do that. Have those two, or any useful information that's at the end of the review document. And then if you go into Lockdown Browser and go into the folder in Blackboard, and you can't see that useful information document, then you'll already have it. It's supposed to be there for you, but on the off chance that it's not because of Lockdown Browser shutting you out, then you'll have it there with you. So do that first. Then you can start your exam, and you have to go through steps. Anybody who's used Lockdown Browser is familiar with it, where you identify yourself, you get a face shot, you show the environment with your laptop or webcam, and then eventually you get started. And once you start, then the timer starts. Now, don't worry about the timer. The timer's there for me. If you need to go more than the timer says, then it's not going to shut you out. You can finish the exam on your own time. It will tell me that you took more time than allotted, and that won't cost you any points, though. Okay, I don't think of any other advice that I could give you, so we'll stop the share, and close the meeting, and I'll post this video as soon as I possibly can.